I'm going to be the presenter today of this talk. Welcome to the Thursday NanoSpin-off talk. Today is entitled Nanoparticles Application in the In Vitro Diagnosis Field, the OPERON Success History. OPERON is a family business company with more than 50 years of experience in the in vitro diagnosis field. So today we have three presenters. We have Tomás Toribio René, that is the managing director of this company. Later on, we will have Laura de Mateis, and we will also have Beatriz Martín, that they will speak about the in vitro diagnosis field, and they are research and development area project manager. So the talk will be more or less 45 minutes, and later on we will have time for questions, okay? So now it is my pleasure to give the floor to Tomás.
Thank you, Maria. Good morning, everybody. I have to say thank you to the Cátedra SAMCA for inviting us to give you this talk about, in my point of view, a successful history of a company involved in nanotechnology. OPERON was founded in 1973 by my parents here in Zaragoza. My father, he is from the Sierra de Albarracín in Teruel. He studied chemistry in Madrid, and he had the opportunity to make his PhD in Heidelberg, in Germany. That's where he met my mother, in the laboratory. After a few years traveling around the world, we established, the family was established here in Zaragoza. My father had a job in a laboratory called Laboratorios Ulta, which does not exist anymore. And in 1973, he decided to found the company OPERON with the help of his brothers and sisters. I'm going to show you a video which is compromising just in 2 minutes the history of the company. And I will make some notes on what we see on the video. So I'm sharing the screen. All right. Let's see if I can play the video. All right. There's no sound, thank you. Yeah. So as I was telling you, this is a startup in 1973. We are located in Cuarte de Huerva, which is very close to Zaragoza. In the very first building, you see this tiny little house. This was the laboratory. And here we have some black and white pictures. The aim of the company was to satisfy the needs of the Spanish market. So the intention was to supply reagents in the field of immunological reactions. My parents bought some rabbits, injected some virus, also the hormone for the pregnancy test, yes, the HCG, and started to extract antibodies. The very first product, which was successful, was a latex agglutination for the detection of pregnancy. The company, the aim was to satisfy the need in the Spanish market, but after 2-3 years, the aim of the company has to be completely changed because the sales in Spain were not enough for giving some work and money for a company of 3-4 persons. So my father decided in 1976, we have to export. And luckily, the very first customer was in the Philippines, who was buying antibodies against the alpha-fetoprotein. This is the first successful reagent. It's already using nanoparticles. In this case, this is a technology called latex agglutination on a slide. The test is very, very simple to perform. You take 1 drop of urine of the pregnant woman, 1 drop of the reagent in one of these black circles, you mix it, and after 2 minutes of shaking, you will see an agglutination because the latex particles are covered with the specific antibodies. So this was our very first successful product, which helped us to get a very good customer in Germany. Remember, I'm half German. My parents spoke German. This was a sort of confidence, and the product was good enough. We were able to sell it to a big company in Europe in bulk. 1 bottle, 1 liter of reagent was good for 20,000 tests. So the product was shipped in bulk to Germany, and they put it in small vials. They formed a kit. They were selling them worldwide with their own brand name. This is an activity that we call OEM, and this is still what we are doing right now. We are selling under OPERON brand name in 50 countries, but we are still supplying to many international, multinational companies. In 1986, we decided to go for monoclonal antibodies. Remember, I told you about rabbits. I didn't tell you, we had also a goat, a lot of work in order to produce those antibodies. But by the 86, we decided we had to go for monoclonal antibodies. And this is a very important milestone. In the early 1990s, we had hired our father of the lateral flow test technology in OPERON, which is Vicente Corbaton, also from the University of Zaragoza. And since then, more than 30 years experience in lateral flow tests. Probably you know already about this technology, but my colleagues, Laura and Beatriz, will tell you more details today. Very important, in order to be competitive, we had to automate our production. This gives us a high quality with a lower cost, since we can save some manual work. In 1996, at the moment we had 7,000 mice, we decided this is no way. We had to change the production of the antibodies. So we bought our very first bioreactor. Nowadays, we have 7 bioreactors. We can produce a huge amount of antibodies. The antibodies we develop in-house, and the intention is to use them in our tests, but the production capacity is so big that we are selling them to our competitors. In the year 2002, we decided also to make our own recombinant antigens. And from the marketing point of view, we decided to go with our own stand, our own booth to the big exhibitions. This is a picture of the Medica 2002, 20 years ago, when we started having our booth. Last week, we had the edition of this year. In 2006, we decided to diversify. We opened a line for molecular diagnostics, and we have a very specific platform, which is it's a hybridization on a strip. We also had another line, which was a PCR amplification and the use of a lateral flow test, but that we had to cancel because we were not successful in the market. 2011, this was a very nice collaboration with Nestle, one of the biggest companies in the food industry. They had a specific need, and we were able to develop a rapid test to cover that need. It was a very nice experience. 2012, the Cámara de Comercio of Zaragoza awarded us a prize for our trajectory in exporting our products worldwide. 2013, we had the first audit of the FDA. We have 1 product registered at the FDA. This is also a very important milestone. 2015, we created a specific department in order to offer a contract manufacturing service. So companies or public institutions have a design of a lateral flow test. We have a specific team to bring that to our company, to convert it in our processes, to adapt it to our automation, our machinery, and then to manufacture and bring it to the market. Usually our customer will take care of selling the product under his own brand name. 2017, we had an export record of 93%. Remember, the company started in order to cover the needs of the Spanish market, but right now it's just the other way around. In 2018, we started with this contract manufacturing service. Right now, more than 5, I would say 6, 7 tests have been developed, manufactured for other companies. Of course, the pandemic came in 2020. We were obliged to do our own lateral flow test. It was a very tough work. We were lucky to produce other lateral flow tests for other companies. And nowadays, the situation is that the market is overcrowded and it is really difficult to sell the tests because the competition is high and the number of tests in the market is amazingly huge. Very important milestone this year. There has been a change in the regulation of the in vitro diagnostics. Now it's called IVDR regulation. OPERON is one of the very first companies in Europe to get this certification. And this is important because the market is going to be more and more complicated every day. Now I also just wanted to show you a document which is not here. No. To summarize, in OPERON, we go from the idea to the finished product. We have an idea, we want to develop a test. We have a team for developing the raw materials, antigens, antibodies. We have a team for R&D. Beatriz and Laura are in this team. There is another group for bringing external designs. This is our manufacturing plant. We manufacture, and then we have our sales and marketing team to bring it to the market. So there are different stages, everything under one roof. We feel responsible for whatever we put in the market. And we look always for collaborations because we are a medium-sized company. We are around 90 people, 80% are women. And well, the good news is that hopefully in 2024, we will be in our new facilities. After staying in Cuarte de Huelva for the last 50 years, we want to start building a new location in Plaza. This is going to be much, much bigger. We can build up to 5 times the size we have right now. So now my colleagues will give you more details about nanoparticles, which I think is the important reason you came here today. Please.
Well, good morning, everybody. What we would like to talk about is the nanoparticles application in lateral flow assays. So, well, nowadays, most of the in vitro diagnostic techniques are based on molecular and immunoreactive assays. So, an immunoassay is a bioanalytical method based on the interaction between the antibody and an antigen. So this reaction has 2 characteristics that makes it very valuable and useful for diagnostic, which is very specific and also it's a high affinity reaction. So A type of immunoassay is the lateral flow assays. So how we can define a lateral flow assay? It is a dynamic technique and also combines the separation of the sample molecules based on their migration on a solid support by capillary flow, and also permits the detection of a particular analyte by means of the reaction between the antibody and the antigen. So in order to understand how lateral flow works, first we are going to make an overview of the main areas that compound this assay, this strip. So here we can find at the end of the strip the area we are going to add the sample. Next to this area, we have another material where we can find the detection regions. Next to this material, there is this area, which is the reading area, where the capture regions are coated and immobilized. And finally, we have another material that ensures the capillary flow. So taking these main areas in mind, we can ask, how does lateral flow assay work? Well, there are different types of lateral flow assays, but all of them share the same concept. Here we can see an example of lateral flow assay. So as we said, first we add the sample to the sample pad material. The sample migrates to the conjugate release pad where the detection region is dry. The detection region is a label that can be a nanoparticle that is conjugated to a biological component. In this particular case, is conjugated to an antibody that can specifically detect the analyte in the sample. Finally, the sample and the detection region migrates to this area, which is the reading area. And here we have the capture region that it is another biological component, in this particular case, an antibody that can also recognize specifically the analyte. And so if the sample contains the analyte, this complex formed between the particle and the analyte is going to be retained in this by this region, this capture region. So we can see two different color bands in this particular case. The red band, which is related with the test line, and also the control line, which is in this example blue, that must always appear because it is a signal that the chromatography works properly. So based on this technology, the reaction between the antibody and the antigen, we can detect proteins, peptides, drugs, and also antibodies, depending on which is the molecule that we are using for the capture region. But in all these types of immunoassays, lateral flow immunoassays, we have the same problem. We have to detect this reaction and also amplify. So for this reason, we use labels. Labels from different nature. For example, fluorescent proofs, enzymes, and nanoparticles. We are going to focus in nanoparticles. Why? Well, because these nanoparticles have specific physical or optical properties to be detected and measured. For example, different colors, fluorescence, F conversion, or magnetism, and so on. So if we would like to develop a new lateral flow test, where here we can see the main points to keep in mind. No? We have to define the product specification, also select the raw materials, select other devices that sometimes are required, and finally think about transferring and manufacturing. So regarding the first point, define the product specification, it's important to keep in mind which is the intended use of the assay, which are the analytes that we would like to detect. It's important to search as much information as possible regarding the analyte, and also sometimes contact with specialist groups in this analyte. We have to know which is the type of samples we have to work with. Also, which is the type of lateral flow we would like to develop. That is a qualitative one, just a positive or negative result. Semi-quantitative is if we require a cutoff value, or even if we would like to develop a quantitative test in order to know the concentration of analytes in the sample. Also important, know the technology, the label that we are going to use to reveal this reaction, nanoparticles or fluorescent proofs, which will be the sensitivity limit of the test. and in the case of quantification, which is the dynamic range or the standard deviation that we would like. Next, we have to select the raw materials. And when we think about this, we are thinking about antibodies and antigen, but not only we are thinking in these regions, also in the labels, other proteins, and in the strip materials. So, well, now we are going to, my colleague, Lara de Matis, is going to go deeply into this area, which is the labels, and in particular in nanoparticles.
Thank you very much, Bea. So we are going, in this part of the presentation, we are going to focus into the use of nanoparticles at OPERON. Nanoparticles, as a general concept, are particles with a size below 1 micron. Sometimes this definition can slightly vary, but at OPERON, we usually use nanoparticles below 500 nanometers, more or less. You have here a figure just to situate about just to place regarding the size we are talking about. And what we need at OPERON regarding nanoparticles we are going to use. Of course, they need to stay in suspension media, in liquid media. And we need them to be able to be linked by us to an antibody or a protein. That is what we call conjugation, as everybody knows. But from this point on, probably we will speak about nanoparticles sometimes, about the conjugated particles. And we need that these particles have an optimal stability in their final nanoparticle suspension, because in this way we can guarantee that they can migrate along the monochromatographic strip in an optimal way. That is very important for the good detection of the analyte and the recognition with it. And finally, we need that the particles present a special intrinsic property that allow them to alert us about the presence of the antigen. At the end, we are speaking about nanoparticles as a tool. Nanoparticles are, we can say that they are always used as a tool in nanomedicine in different fields. Here are some of the most known application of nanoparticles. In our case, we are going to speak about nanoparticles as support for biomolecules to be included in a diagnostic device. The diagnostic device, as already introduced by my colleague, is this one we are speaking about. And what we need exactly from these particles? On one hand, we need intrinsic properties of the particles. These are related to their nature, their size and colloidal stability, sometimes their geometry, or the nature of their surface. But we can also think about acquired properties, because we can take a nanoparticle, we can modify it by modifying its surface functionalization with biomolecules. That is what we want, for example. We can also combine different materials. We can create a surface coating with a different material for different properties. Or even we can control the aggregation depending on the properties that we want. In all cases, when intrinsic properties join the acquired properties that we want, we obtain a multifunctional support. And all the time during our processes, we are going to control both intrinsic and acquired properties through in-process tests, because it's very important, the possibility, and to know if our processes are going as we want. The main properties that usually routinely we are controlling, we are checking, are the concentration, the size, and the nature of the surface. The concentration is important because it's a parameter related to the reproducibility of our processes. But also, if we are putting a molecule on the surface and we want to check this ratio, it's an important factor to control. The size, because it's related to the colloidal stability. I mean, the method, the technique used to measure, to analyze the size, can give also the information about the colloidal stability, as most of you know. So it's very important for our application. And finally, the nature of the surface is something that can be controlled using the information that is given by different techniques and put all the information together most of the times. And it's something that we can use to know that the process has been successful. All the techniques that I have put here are the most common techniques that are used to analyze these properties. Most of them we can use at OPERON. Probably the only one that you can use is the electron microscopy, but this is not a technique that you can use for ordinary processes in a manufacturing way. So this is why we don't take it into account. We are going now more in depth about the use that we do of nanoparticles. So as Beatriz already said, when we are designing a new product, we have to choose the label that we want to use. That means the nanoparticles that we are going to select depends on the test, the kind of test that we want to develop. At OPERON, we use different particles the most used particles are the colored latex, gold nanoparticles. Sometimes we use carboxycellulose nanoparticles, and now we are developing new products using fluorescent nanoparticles. Once we have the particles, we suppose that for the same reason, depending on the test that we are going to develop, we have chosen the molecule that we need to put on the surface. It can be an antibody, a protein, a peptide that you have here as an example, but it can be also a chemical drug or whatever. If there is a reaction, a recognition reaction related with this molecule. And once we have the nanoparticle linked with the nanomolecule, we can generate different recognitions with the molecule, the capture molecule that we have on the membrane. So you have, again, only some examples here, just for you to see that there are different combinations that we can have. It always depends on the kind of product that we need to develop. And sometimes we can, during the development, we can test different strategies to know which one is the better one that we need to choose. So this is translated to this situation in the strip, and also a colored line in the case we are using, for example, the colored latex, that is the particles that I will use for my example. This is a real product. This is a strip that contains a lot of information that can give us a lot of information because it's a multi-analyte lateral flow test. This is a product that is able to recognize, in particular, 3 parasites. So you can see that this is an example. We have 4 lines of different colors. One of them is the control line that it always appears, and the other 3 are able to recognize, to detect 3 different analytes, with different strategies. I mean, each particle have attached a different biomolecule that is able to recognize only one analyte. So why I put this example? Because you have to think that behind this strip with 4 different colors, we have a lot of work to optimize 4 different nanoparticle suspension that are the ones that will go inside the material. And each one of them needed to be optimized in its process of conjugation. I don't know if you are familiar with the concept of conjugation of molecule on the nanoparticle surface, but I will summarize it. We use particles that have a functional group on the surface, and we want to link a molecule on the surface. This is possible using a cross-linker that can be, well, let's say there are a lot of cross-linkers. Because you have a chemical structure with a reactive group on a surface, or on one hand, sorry. You have another reactive group on the other hand of the molecule with a spacer. The spacer can be shorter or longer, or even it can include a label to know if the crosslinker is in the place we want it to be. And the reactive groups on the hand, it can be the same group or even different groups, depending on the biomolecule we are going to attach. So once we have selected our crosslinker, the first step is always the reaction of the crosslinker with the particle. And after that, we add the biomolecule, and the biomolecule reacts with the other hand of the spacer if we design the process correctly, of course. But all this process lasts a lot of time. At OPERON, especially, in particular, this process lasts 1 working day, 8 hours. These are the main steps without all the details of each one. You can see that there are the steps that I previously mentioned. There is also an optional step that appears here. That is the blocking of the surface. This is optional because sometimes it's needed and sometimes it is not needed. And what does it mean? That sometimes, depending on the amount of biomolecules that we add to the reaction and the amount of reactive groups that we have, we can have a balance in which on the surface we still have reactive groups, free reactive groups. So in this case, maybe it can be useful to attach something that is not able to produce recognition with the antigen, but that can avoid that this group reacts with some of our chemicals in the formulation or in the sample. After that, we have our final nanoparticles. In the case of the strip that we were talking about, we have 4 different nanoparticle suspensions. So how we use these particles for the strip? First of all, we have to mix them, always checking all the parameters that we established to check along the process. So when we arrive at the end of the process with nanoparticles characterized, the concentration, and all the checked parameters, so everything is okay, we can mix them together with a formulation solution that contains stabilizers and blocking agents in order to be able to stay in contact with the sample without causing any underside effect. So this is the mixture that finally go on the conjugate path that we showed in the strip. And regarding all the conjugate path and all the other materials that compose the strip, my colleague will explain you better.
Okay, thank you very much, Laura. So, well, coming back to this slide, next we are going to talk about the strip materials, and that we just would like to show you a short overview about all the materials that compose the strip. So, well, we need to talk about the backing, which is just here colored in orange. It is an adhesive card where the strip materials are fixed and assembled. And just the function is just to make it possible to cut the materials into strips and also make easy the handling of the strip. So the main material, the main compound is the adhesive, because we really don't want that this adhesive can interact with the materials of the strip and change its properties. Well, as we commented before, this is the sample pad material is an absorbent material where we are going to add the sample. So it is just the woven meshes or cellulose fibers that promote an uniform and controlled distribution of the sample into the conjugate release pad material and also prevent the floating of the strip. So the key properties. The same in all the materials. We really don't want non-interactions between this material and the analyte and the target. So it's important to select a material that has the bed volume according to the sample volume that we are going to use. Also, sometimes it's necessary to pre-treat the material in order to reduce non-specific binding and also increase or reduce the viscosity of the sample, and sometimes, mainly if you are working with urines, in order to control the pH. Also, when we are working with whole blood samples, it is necessary to use a special sample bag material, which is a blood separation filters, mainly composed by glass fiber, and it has an additional function, which is get an efficient separation of the red cells from the serum and the plasma, because we really don't want that the red cells coming into the membrane, and this separation must be done avoiding the hemolysis of different red cells. Otherwise, the hemoglobin comes into the membrane and die the membrane. Well, the next material is the conjugate release path material, where we are going to write the conjugate, which is the detection region. So this is mostly composed with non-woven filters with different nature, for example, glass, cellulose, plastic, and the main function is to ensure a uniform transfer of the sample and the detection region into the reading area, which is the membrane. So also, it's necessary to preserve the conjugate in a dry state and also in a stable state, and permit the weighting of the conjugate. Key properties, again, non-interactions with the conjugate, the colloid, and also the analyte. And it's important that this material has a consistent bed volume in order to have an homogeneous distribution of a conjugate into this material and makes the test more reproducible. Also, it's important to favor the suspension and homogeneous release of the colloid. Sometimes it's necessary to pre-treat because these materials sometimes are really hydrophobic, so we have to pre-treat with detergents or surfactants in order to make it more hydrophilic and favor the suspension of the detection region, the colloid, and also its stability. And sometimes reduce non-specific interactions with the colloid and also with the sample. Now the membrane. Well, the membrane is one of the most important elements in the lateral flow assays because here it is the reading area. So it is the place that we are coating the capture regions and we immobilize them. So mainly it's composed by a polymer that sometimes usually is treated with surfactants and detergents in order to make it more hydrophilic. And in lateral flow assays, we usually use nitrocellulose membrane. So the nature of the polymer determines the forces in order to bind in the protein. In the case of nitrocellulose, are electrostatic forces. Here you can see the structure of this nitrocellulose fiber at microscopy view. And it's important to know which are the main parameters that characterize the membrane. So the first one is the capillary flow time. This is well, it's usually that most of the manufacturers make you available this parameter. So in order you can compare between different membranes, and it is defined that the time required for a liquid that is usually water to weak a defined distance, usually 4 centimeters. It's also another parameter is the pore size, the porosity, the thickness, and what is the relationship between these parameters? Well, in an ideal situation, a large pore size porosity means high capillary flow time and less nitrocellulose per square meter. For us, it's really important to know what is the protein binding capacity of the membrane. So it depends on membrane properties that we just talked about them. Also molecular properties regarding the protein structure, diameter, size, also the isoelectric point, and also if this molecule is hydrophilic or hydrophobic. And also coating regions are going to influence, because if we are going, if we use, for example, chaotropic regions, this can interfere with the binding of the protein. And finally, the aim is select a membrane, depending of what are our requirements regarding sensitivity and reproducibility. So, how this parameter influence in these two issues? Well, high capillary flow time means a fast membrane and less protein binding capacity. So therefore, we will have tests with low sensitivity and usually low reproducibility. On contrary, low capillary flow time means a slow membrane, high protein binding capacity, and therefore the development of high sensitivity and usually high reproducibility. And finally, regarding the membrane, sometimes it's necessary to pretreat also this membrane. So we block the membrane after coating with the capture reagent in order to, well, reduce the background, reduce non-specific interactions, for example. Here in this area, we have the absorbent pulp material, which is just an absorbent material that controls the total volume taken by the strip. So in this way, can improve the sensitivity of the test, also reduce the background, and prevent a backflow of the sample and the colloid of the detection. And well, finally, we would like to comment just that sometimes it is not mandatory, but in OPERON we usually use it. You can use a cover tape, which is a transparent adhesive fixed into the strip, so ensure a perfect contact between the materials and the capillary flow, and also protect the strip materials, because the membrane is really a fragile material. So again, non-interactions between the adhesive and the strip materials are required. So continue with other devices that sometimes are required. We just would like to comment that we can use a cassette, which is a plastic device where we can put inside the strip, and we are going to use it mainly if in the case you are not using a cover tape, because we can use cassette with pressure points that ensure the perfect contact between the material. Obviously, these pressure points don't have to block the chromatography. And also it can protect the strip materials. And for the final user, is quite useful because you can point where the sample must be added and also where the test and the control lines must appear. Another device that can be used is a reader. You know that now in the market there are a lot of readers that are portable devices that can read and interpret the result in the strip. So obviously it must be adapted to the label we are going to use and the property that we are going to detect, color, fluorescence, whatever. And in the case of quantitative tests, is mandatory, and also in qualitative ones that are function with fluorescence, but it's also really useful in the research and development phase. So, and finally, we have to think about transferring and manufacturing. It's important to keep in mind because, well, in research and development, we are working in batch. But finally, we have to go to manufacturing, to a reel-to-reel. So regarding the materials in research and development, we are working with cards. But finally, we have to work with rolls. So obviously, we have to select the best performance materials, but also materials with a good tensile strength, easy to handle, and so on. And it's also important to scale up the process. Obviously, the conjugation of a conjugate and the preparation of the coating regions and all the regions in general. So finally, you require a proper equipment in order to coating the membrane, dispense the colloid, assembling the materials, and also several pick-and-place platforms in order to insert the strip into the cassette and so on. So, well, finally, you have the product ready in the market. And this is just some examples, quite similar, but as you can see, uses different accessories like different vials, pipettes. So these other materials has also to take into account. And as conclusions, well, a lateral flow is a simple technique, but with a complex global design. It's really important to correct definition of the product specifications to have a good design. All the strips are, all the materials of the strips are really important. So good cooperation between the strip materials are essential to a proper lateral flow assay performance. Compatibility between nanoparticles and the strip materials are critical for the successful assay. And new or better nanoparticle properties, well, we think that can improve the capabilities of the lateral flow assays. So thank you very much for your attention.
Well, thank you very much, Tomás, Beatriz, Laura, for being here today. I think that it's been like an amazing talk. Thank you to Cátedra Sanca for bringing you here. You have seen that we have a full aula, and also have people that couldn't come. I think that it's been like amazing to see a family company from the beginning to the product. So now I think that is time for questions. So please don't be shy. I think that is a perfect opportunity you have here, like 3 experts in IVD diagnosis. So is there any question?
I have 2 questions for you. First, thanks to all of you. And I have some questions about how the polyexpressity index affects to the chromatography when you are using 2 types of particle, one for the detection of the test line and the other for the recognition of the control line.
Thank you for the question. It's very interesting because it's an issue that can occur. When we start optimizing the process of the conjugation of the molecule to the particles, it can occur that depending on the molecule, the first trial, we have aggregation of the particles because we have non-specific interaction between the particle and the biomolecule. And this is quite bad for the assay. Why? Because as we said, the materials that we have on the strip have a limited porosity, and we have the capillary flow with a certain capacity. So if you have an aggregated particle, it is sometimes it can get stuck on one of these materials, but it also can occur that depending on the cause of this aggregation, you can have undesired interaction with the sample. For example, you can have this can result in a false positive result or defects that we need to avoid because it can affect on directly the result of the test. This on one end regarding the aggregation of the particle itself and the migration of the particles along the strip, but it is also detrimental for the recognition with the capture molecule, because it's not the same if we have particles that we selected for its diameter. It's not the same if we have 40 nanometers gold nanoparticles or a 300 nanometers latex particle. So the conjugation process depends a lot on this size. Once the particles arrive to the capture molecule, it can occur that depending on the aggregation, the detection, the first step, which is the detection of the analytes, is is affected, so there is less analyte on the particle because the surface is not accessible. The reaction cannot occur because if there are 4 particles together, the surface inside is not available for the antigen to reach the biomolecule that we have, even if the processes of conjugation has occurred in a correct way, and the aggregation is in a following step. You know, there are a lot of cases that can affect all the steps of the process, and most of the time you can have some defect that finally you see on the strips, and you have to trace all the process, what has occurred, to know exactly why you have a defect, because it's not so easy to understand the first time. I hope.
But when you use 2 type of particles to the different recognition.
Sorry, I cannot hear you.
When you use 2 different particles for the recognition of the 2 lines of the test line,
Yes.
you have to use them with the same set potential, with the same
No.
index. They could be different, right?
Okay, sorry, I'm going to repeat the question because I think that in Zoom they are not listening to it. I think that Antonio is asking if you have 2 types of nanoparticles for the test line and the control line, if they have to be exactly the same in terms of polydispersity, and zeta potential, and
We always need that the polydispersity index is the optimal one. I mean, ideally monodispersed particles. This is the objective, the goal. In terms of the surface and the characteristic of the particles, it's not a requirement because you are conjugating with different molecules. So you have different needs from these 2 particles. It depends on the molecule.
And my other question was about the membrane. When you were talking about the blocks of membrane after the deposition of the agents, for example, the antibody, and what kind of compounds do you use to block that membrane? Organic ammonia or some protein from milk?
in that the other question regards the blocking of the nitrocellulose membrane, if you use like serum albumin or other proteins like from the milk.
Yes, it's very useful to use different proteins in order to block, but depending, you have to adapt the composition to your requirements, because obviously sometimes you have to block the membrane because you have non-specific interactions with the analyte that you are going to detect. So depending of this of the interaction, the nature of these interactions, you use different components. So you can use also some surfactants, but mainly proteins that can be well, even BCA or casein or whatever. So different kinds of proteins, and you have to adapt this composition to this particular case. Because, so it's really important that you block the membrane after the coating, because otherwise you can lose the antibodies. For example, if you are coating antibodies in the membrane and the membrane is not completely dry, you have a problem if you block the membrane. So, well, the composition, it is not a universal composition, but yes, can contain, as I said, proteins, surfactants, detergents, sometimes polymers even, depending.
To protect the two test lines, is there another way that not using a needle, for example? Is there any compound that could be used to protect the antibodies in the test line and the control line?
Yes. Anthony
Yes.
is asking if, because I need to repeat that.
Okay.
If there's like any other way of protecting the test line instead of with the film with other components or something to avoid the losing of the antibody. No?
Well, the truth is that sorry?
Degradation.
The degradation. Well, the degradation is more related with the environmental conditions that you are storage the strip. So we usually storage the strip in conditions with non-humidity. So we poach the strip into a box, a bag, with silica gel in order to avoid this humidity that can favor the denaturation of the proteins that were coated. And but in the from physical damage, you know, I just know the existence of an adhesive, a film that you can put with this material you can cover the membrane and the other materials also. And also use a plastic cassette, which is this plastic device in order to avoid the contact of the membrane with other materials. But finally, we usually we poach this assay into aluminum box bag with the silica gel.
Thank you so much for the presentation.
You're welcome. Thank you very much.
Thank you. Is there any other question? No? I have a curiosity while you are thinking. How long does it take on average since you decide to make a test until you commercialize? Oh.
It can take long, well, it depends. It depends very much on the complexity, but we have done tests in 6 months, and normally it's 18 months, 2 years. The 6 months was for pandemic, of course. No? For pandemic time. Yeah, well. No, one of the very critical points, apart of all these technical aspects which you have been explained today, is the regulatory matter. So there is a lot of work to do on the field, demonstrating that the test is really achieving those specifications that you are claiming. That's also a complex part.
Okay, so thank you. So, any other? Clara, please.
I'd like to thank you all for this presentation. Well, my question regards the readers. And well, as Laura already know, and I also share all the methods of trying to use magnet methods for more sensitive. And I know that what we do that subject to it, but still I see now and then many articles trying to make use of my properties and then that the types of concepts and I would like to know, as we're not working like that, the real work, if there are any of these alternatives in the real market.
I think I can reply to your question. Your question is regarding magnetism, just in case the audience in the internet. So, right, for the last 15 years at least, there's been a lot of publications, a lot of work in that area. I know about some American companies trying to bring this possibility to the market. I remember they had a huge instrument like this, and I was following them for a while, and they never had a profit, always losing money. So I heard about new low-cost readers using magnetic particles. I have the impression that this is coming back. Yeah.
Yes, but I'm aware
Yes, but it looks like the electronics have made some progress, and now you have even low-cost electronics that allow you to make a very fancy pocket reader using magnetic particles. Well, I think the technology is there, but let's see if somebody brings it soon to the market.
Okay, thank you very much. I think that I don't know if anyone in the Zoom has any question. Well, if not, if you don't have, I think that we need to thank again Tomás, Laura, and Beatriz for being here. Also, Cátedra Sanca. I think that it's been like a fantastic talk and an amazing example, really. Thank you very much for being here today. Thanks all of you for coming, and this thanks everything.